All right, hey again. So this is the second worksheet, I guess. Whatever. This is the DTDS worksheet. So discrete time dynamical systems. That is such a mouthful. So DTDS. And what is a DTDS? It's what happens when you just measure a variable at regular time intervals. Okay. So measuring a variable, that's your dynamical system, and regular time intervals, that's discrete time. All right. So we're going to get a list of measurements. There's sort of like the first thing, which we call M0, and then like the first time interval goes by, maybe a minute, maybe a month, maybe a year, maybe a second, but that's our next measurement, and then our next measurement, and then our next measurement, and then our next measurement. So we could also call this a list. Okay, that's all it is. All right, now I have a bunch of typos on this worksheet. I'm so sorry. I didn't have a lot of sleep when I made it, and I was editing one from last year. So, all right, here we go. Baby's born weighing 7 pounds. Hey, that's a first measurement. Look at that. So, in fact, because it's the weight, I'm calling that W0, the initial weight, which we could also call the weight at month 0. So, whether you want to think of it as an input or just think of it as telling you when it happened, it's all the same idea, and that is 7 pounds. So, sort of the first typo is this 100 should not be there. It's a 7. All right. Similarly, we're not talking about how much Sally has in savings. That's from an old one. Okay, so a baby's born, it weighs 7 pounds. It gains 1.5 pounds every month. Let M denote the months that have gone by, and then W of M be the weight after M months have gone by. Now, you could also, I wrote it down like that, but we could just say WM is the weight at month M, okay? So at month 0, aka birth, 7 pounds. At month 1, well, it's going to be 7 plus, in fact, let's just do at month 1, the weight at month 1 is 8.5. At month 2, the weight at month 2, let's see, I add 1.5, that's 10. At month 3, the weight at month 3, I add 1.5, that's 11.5. Okay. Now, what the heck is WM plus 1? So, intuitively, it's sort of the weight next month. But technically, it's the weight at month M plus 1. Okay? So, W doesn't know any better. Whatever number you put there, it goes, oh, that's the month. Let me tell you the weight. Okay? And so M represents some number. It's, the month. And if I add 1, it's still a number. And so this is just the weight at the month M plus 1. And so when M is equal to 0, M plus 1 is equal to 1. And so this is just W1, which is just 8.5. Okay. And you'll see why we're doing this in just a moment. But for now, we're really just putting these values here. So this is 10. This is 11.5. And now what goes here is W4. So W4, I have to add 1.5. So that becomes 12 is 13. All right. So now we need to make 2 graphs. And the first graph, so we're going to have a X and a Y pair. All right. X is M. And Y is, and there's another typo. Damn it. This is WM. I used to have an amount in savings, and now I have a weight at month M. So sorry about that. All right. So this is the weight at month M. All right. So that means I'm looking at these first 2 columns, and I'm plotting these values here. So I have 0, 7, and then at 1, I have 8.5, and at 2, I have 10. And in fact, it's all going to lie on this line here. And at 3, I have, this is 3, 11.5. Cool. All right. So that's the first graph that I'm looking for. Let's clear this up. Boop. 7. Great. Now, if I just look at these 2 columns, though, let me label, this is something called a solution function. Okay. And then we're also going to have something called an updating function. So updating. And it's called that because this is how you update your list. You know, when I computed 8.5, all I did was add 1.5 to 7, right? And when I computed 10, all I did was add 1.5 to 8.5. So when I update my list, I'm performing something. I'm performing a function. And the input for that function is a weight, and the output for that function is a weight. And so the reason why I have these two columns side by side is because now this plays the role of x and this plays the role of y. So what I'm saying is your x-axis is the weight at month M, which is a little weird to think about because M could be any month. It doesn't matter. It doesn't matter. What matters is the weight. So like, for example, right here it's 7. That happens to correspond to W0, but it doesn't matter that it corresponds. It's just a weight. It's just 7 pounds, okay? It doesn't matter what month that took place. Just if the baby's weight was 7 pounds, okay, fine. The vertical axis is the weight 1 month later. The weight at month M plus 1. Well, if the weight was 7, then 1 month later, it's going to be 8.5. And so we get this thing, okay? Now, if the weight was 0, then 1 month later, it would be 1.5, right? Now, the weight's not 0, but whatever. That the algorithm we did to sort of, go here or go here, however you want to think of it, to go from 7 to 8.5, to go from 8.5 to 10, to go from 10 to 11.5, to go from 11.5 to 13, right? What we've done is whatever the weight was, we added 1.5, and that's the new weight, Wm plus 1. And I'm going to use subscripts or sort of the typical function notation interchangeably. Okay, they mean the same thing. And I'm sorry, I know it's confusing at times. I'll often use subscripts because it's less writing, right? I don't have to write these parentheses. So, all right, I have this function here. That's my updating function. And, all right, and you look at them and you go, well, they're both lines. Why do I care? Whatever. All right, well, that's sort of the point of this last little question. So assuming the trend continues, what is the baby's weight after 1 year? All right, well, how would you solve this? So 1 year is 12 months. So you're likely, if you know what Wm is, yeah, sorry, this is also W. If you know the solution function, then you can just plug in 12. If you don't know that, then you're probably going to have to continue this. So we have 4. We can go to 5 and 6 and 7 and 8 and 9 and 10 and 11 and 12. And you just have to keep doing plus 1.5, plus 1.5, plus 1.5, right? And all that stuff. So can we figure out the solution function? Well, let's see. So at 1, so 1 month later, it was 8.5. At 0, it was 7. So the slope of this line, when I go over 1, I go up 1.5, right? So my change in weight is 1.5. Change in months is 1. So my slope, top over bottom, is 1.5. So W, function of M, is 1.5 times the number of months, plus, and my y-intercept is 7. So here's a solution function. So we could plug in 12, and we get the weight, which turns out to be 25. Yeah, it'd be 18 plus 7 is 25. Okay. Now, in order to do that, we had to find the solution function, and that's not always so easy. Okay, and that's one of the points that we're going to make as you go through this activity. All right, so an updating function is what you do to update your list. So I add 1.5, add 1.5, add 1.5. My updating function, you could think of it as the function y equals x plus 1.5. Okay, that is what I've graphed. It's just the variable x. What does that even mean? It's my input variable. It's some kind of weight. And the output variable y, it's some kind of weight. And the input represents the weight at some month. And the output represents the weight 1 month later. Okay, so anyway, it's a little weird to think about, but I'm just going to introduce it now. All right, so here's a web work problem. It's the exact same idea. Here's our updating function. So we're measuring some length this time. And what's going to happen to the length? In order to get the next one on the list, well, you subtract 1.7. All right, fine. So if we begin with 13.1, let's subtract 1.7. So that'll become 12. It'll become 11.4. All right, so what are we looking at? Months, years? So don't know. All right, 1 time unit later, we're at 11.4. All right, if I subtract 1.7, it'll become 10, it'll become 9.7. That's happens there. And so on and so on. So like we could fill these out, right? Okay, find a solution function for the system. All right, here's the tip. Here's the tip for finding solution functions. Okay. So let's write out how to find the first few measurements without simplifying. And you want to use names, not numbers. Okay. Well, you'll see what I mean in just a moment. Names, not numbers. Okay. So how do we find L1? Well, we take L0 and we subtract 1.7. How do we find L2? Well, we take L1 and we subtract 1.7. Okay, but without simplifying, write down the computation you would have to do. So what would you have to do to L0? So in other words, how would I find L2 using L0? And the trick is, well, L1, wait a second, this is L1. So we can just substitute that expression in for L1. So this is L0 minus 1.7. Okay, this thing here is L1 minus 1.7. Now, L3 is L2 minus 1.7. So let's substitute. Here's L2, right? This whole thing. So we're going to substitute that in here. This is L0 minus 1.7 minus 1.7. So there is my L2 minus 1.7. That was this thing. And then you look for the pattern. And the pattern will depend on the subscript. There should be something clear that happens here, right? And I hope you can see that. So do they use T? They do. Okay, L sub T. Well, it's going to be L0 minus, and then there's T copies of 1.7. Okay, right here I have 1, 2, 3, and there's a 3. Here I have 1, 2, and there's a 2. Here I have 1, and there's a 1. And in fact, right, L0 is L0 minus 0 copies of 1.7, right? So, okay, we found something that works. This is our solution function. So we'd have, and then I can finally plug in the number and not the name. So I could finally plug in 13.1. So in other words, sorry, I boxed the wrong thing. Boop. L of t, which you could think of as the length as a function of time, because that's what it is, we're just doing a subscript, is the initial length minus, and I'm going to write it like this, 1.7t, but right, this is just t times 1.7, and this is just L0. So the way I found the formula was by writing out the computation I'm doing, and I try and leave L0 in as long as possible. Right? So this answer would be 13.1 minus 1.7t. And then plug in 20 for t. All right, fine, whatever. Okay, so, up until now, we only looked at updating functions of this form. So what do we mean? We mean the next measurement is sort of your current measurement plus some number, right? So here, that number was negative 1.7. Here, that number was positive 1.5. But in any case, the next anticipated measurement is just whatever your current measurement is plus some number. Okay. How do your measurements change in this case, i.e. what pattern? Okay, I think what I was going for here is just sort of M1 is equal to M0 plus C. M2 is equal to M1 plus C. And then we want to substitute what M1 is. It's M0 plus C plus C. I should have just said find a solution function. What is this? Probably don't even worry about that. Let's just find a solution function. So, hey, there's two C's here. This is M0 plus two C's. And M3 is M2 plus some number. Well, M2, hey, here it is. It's M0 plus two C's plus that C, right? Because this is just M2. Wait a second. That's M0 plus three C's. So, in fact, the solution function in f of t is M0, that's some number, plus T many C's. Okay, I know that looks weird. So M0 is just whatever your initial measurement is. So in that last web work problem, it was 13.1. In the baby problem, it was 7 pounds, right? It's just whatever your initial measurement is. And then C is just the constant that you add on in order to get the next measurement. So in the length problem, it was negative 1.7. In the baby problem, it was positive 1.5. And in general, the solution function, when your updating function has this form, it's going to be a line. It's sort of like, it's mx plus b, but there's no x. We're using t. This is like an x, and c turns out to be m, and then this thing here turns out to be b. Okay, it's mx plus b. It's a line. We're just introducing so many new names, but I promise it's not new ideas in the sense of like this is the equation of a line. All right, I know I'm going fast. It's because we're going to work on this in class as well. So, all right, let's do something more interesting than a line. So, common occurrence is for the updating to the change to be proportional to the amount of stuff. Okay, and in fact, this is what it means to grow exponentially. This is the defining characteristic of exponential growth or decay. So, like if a population grows at a rate of 1.5%, then like if you have 1 million people, okay, 10 to the 6, then the amount of new people you expect is sort of 0.015 times that. This is how many new people. So this is the growth. This is how much new stuff you got. But if you only had 10 people, then the amount of new people you expect is less than one person, right? Because this is only 0.15. So the amount of new stuff is proportional to the amount of existing stuff. When a lot of stuff exists, then the new growth, it's this product, right? And remember proportional? Remember how that was y equals mx? Or in this case, we could say the new stuff is the old stuff times some number, times some kind of constant, okay? This is what it meant to be proportional. It's y equals mx. That was what it meant to be proportional. You just multiply this by some number, and that's your new thing. Okay, so when the change is proportional to the amount of stuff, that's what it means when we say exponential growth. Okay, so let's look. All right, a population grows by 50% each year. The initial population is 1,000. Fill in the table. All right, fine. So time 1, time 2, time 3. So what do we do? Well, look, the new amount is the old amount, and okay, grows by 50%. So look, okay, the growth. I should just write it like this. Look, times 0.5. So we're imagining no one dies, Okay, so this is just sort of like what already existed. But then the growth, okay, the growth is 50% of what exists. So the total new population, sorry, when I was talking about growth earlier, I was sort of only looking at this part, right? And so I wasn't talking about the new population. But now I'm talking about the new population. So we have the stuff that's already existing plus the new stuff. So what is this? This is 1.5 P of t. So my population 1 year later is my old population times 1.5. So 1.5 of 1,000 is that. 1.5 of 1,500. Oh goodness. Let's see. Half is 750. So I guess we got 2,250. Ooh, half of that. Oh my goodness. Add 125. That's 375. Add 1,000 is 3. I hope that's right. I don't know. And then you can kind of just put these here and here and here if you'd like. So this is 1,500. This is 2,250. This is 3,375. I sure hope that's right. Okay, and how would we get here? We would take 3,375 and we would multiply it by 1.5, which I don't feel like doing right now. Okay, so the updating function is what we do to update our list. It's this algorithm here. We call it an updating algorithm if you'd like. Okay, you take, so this is updating. Whatever your current measurement is, you multiply it by 1.5, that's going to be your new measurement, right? That is how we updated it. That's how I went down my list, right? I promise the name makes sense. It's just we're not used to seeing these labels here. Like, you should think of this as y equals 1.5x. It's just x has this really complicated name, but it's just a name. It's just a name. It represents the population. This represents the population a year later, but that's fine. Okay, find a solution function. Find a solution. So let's go back to what my old tip was, which is to just kind of like write stuff out where you use, here's the mantra for solution functions, names, not numbers. Okay, we're going to do this a lot for discrete time dynamical systems. So how do I find the population in the first year? Well, I take the population that was initially there and I multiply it by 1.5. How do I find the population in the second year? Well, I take the population in the first year and I multiply it by 1.5. But wait a second. Here's the population in the first year. Let's plug it in. So I have 1.5 times 1.5 P naught, which, just to emphasize the pattern that's showing up, that's 1.5 squared P naught. How about in the third year? Well, it's 1.5 times the population in the second year. Population in the second year, that's this. Plug it in. But look, that's 1.5, and then we have 1.5 squared. That's going to be 1.5 cubed times the population initially. And now you kind of stare at this and find the little pattern. Here's a 1, there's an invisible 1, here's a 2, here's a visible 2, here's a 3, here's a visible 3. The population at time t is 1.5 to the tth power times the initial population. Okay, that's my solution function. Okay, and what's the initial population? It's 1,000. So this is 1,000 times 1.5 to the t. Okay, so this is sort of what I meant when I wrote f of t here, right? Notice the only variable here is t. When I write p0, that's not actually a variable. That's a number. That's 1,000, right? It's not changing, it's just the initial population. So again, solution function, you sort of write out how you're finding these things in terms of P naught, or whatever your initial measurement's called. Okay, here's the exact same idea. You can try this, but we'll just, well, look. All right, to update, you multiply by 3. So my initial is 5, multiply by 3, that's 15. Multiply by 3, 45. Multiply by 3, 135. Dope. Find a solution function. Well, b1, that's 3 b naught. b2, that's 3 b1, which is 3 times 3 b naught. b3, that's 3 times b2, which is 3 times 3 b naught. Right? Hopefully you're catched on to what's happening here. Here's b1, here's b1, but also here's b1, so I just substituted in, and that's where this thing came from. b2, that's this. That's all of this, so that's all of this. Right? And hopefully you can see that bt is just going to be 3 to the teeth power times b naught. And you go, hey, b naught's 5. This is 5 times 3 to the teeth power. There it is. That's the answer for that. Okay, cool. And so this, what's going to happen? So I'm just generalizing the above, right? I didn't have to call this initial population A. I could have just called it B naught, but whatever. If you're catching on to the pattern, the answer is going to be this, where I have like, there's some common multiple that I use to update, right? So in my first problem up here, that multiple was 1.5 because I grew by 50%. In the Weber problem, that multiple was 3. But in general, there's just some multiple, and then bt. And so if you work it out, like b1 is c times b naught, and b2 is c squared times b naught, and b3, and why is that? Well, it's c times b1, which is c times b naught. Right? It's the same stuff I've been doing. And so if you're okay with that, then you can kind of see how this gets here. At least we can see the t's match. And then that's why I made my comment about A. I kind of regret doing that. It's just what I'm calling the initial, right? Here A was 5, and here A was 1,000, okay? So it's just whatever your initial population is. And so B0, I could have left it, I could have left it like this. It's B naught times C to the T. So this is good, this is good. They're saying the same thing because that's just the same number there. Okay, so these are the two sort of, you should absolutely know these solution functions by heart. So there's the exponential one, right? T's in the exponent. Oh my goodness, sorry about that. T's in the exponent. There's the linear one, which I'm already losing. Sorry, it's late. There's the linear one. All right, and then there's this weird mixture. So let's start building some discrete time dynamical systems and see how mixtures sort of naturally happen. So, all right. And you might be thinking, like, why do I care? Why we use this? Well, all right, medication, right? Medication. All right, in general, finding a solution function is not easy. Yeah, that's true. We've only looked at 2 special cases. Yeah, that's true. All right, so here's a textbook exercise. I edited it a little bit just to make it a little smoother, in my opinion. So, all right, a patient takes like a 10 milligram pill of some kind of medicine. So we're just going to assume 10 milligrams of medicine, it's running throughout their bloodstream. They're going to excrete 60% of it every single day, and they're going to take a 3 milligram pill each morning. All right, so at time 0, how much medication is in their blood, and then what about a day later, right? So at time 0, there's 10. And what about a day later? Well, they excrete 60%. So it's sort of like 10 minus 0.6 times 10. But if you factor out that 10, we have 1 minus 0.6. In general, 40% is left over, right? So we have 0.4 times 10. And then they pop another pill, so plus 3. Okay, well, that's 4 plus 3 is 7. All right, and well, 40% of 7 is going to be left 24 hours later, and they pop another pill, and that's 5.8. That's 2. And ... Hopefully you can see at time t, they're going to have some amount. Okay, what I'm calling it M, medicine at time t. And the medicine the next day, well, it's 40% is left over of what was there, and they pop another pill. This is the updating function for our discrete time dynamical system. Right, so what is the updating function? There we go. So that's my answer to part B. Part A, I wanted to make a table, so I did that. Find a solution function. Ugh, gross. All right, pray for me. I don't know. We'll see how it goes. Okay. All right, let's do the tip. And this is where, I think Jeff wants you to guess and check, and I just think that's so hard. And in order to actually do this, it probably requires geometric series, which you don't know. So maybe there's a slick way to do this, but whatever, here we go. All right, M1 is 0.4 M naught plus 3. M2 is 0.4 M1 plus 3, but that's 0.4 times 0.4 M naught plus 3 plus 3. Okay, so let's see, we got 0.4 squared M naught plus, and now we sort of have 1 point, I'm going to write it like this, 1 plus 0.4 times 3. Now I'm sort of cleaning it up, and I'm cleaning it up in a way that I know a pattern is going to appear. M3 is 0.4 M2 plus 3. This is 0.4, and now here's M2. Let's plug that in. 0.4 squared M naught plus 1 plus 0.4 times 3. Right, all of this was just M2, and now we have to add 3. Okay, so we distribute the 0.4, and we're going to have 0.4 cubed M naught plus, and now 0.4 times 1 is 0.4. 0.4 times 0.4 is 0.4 squared, and then there's this extra 3. So like we have a 3, we have a 0.4 times a 3. That's when we do this times the 1 times the 3. Oh, I feel like I should just write it out. Sorry, let me just write this out. Okay, let's look at what we have. I'm going to distribute the 0.4. It goes here, it goes here. I have 0.4 times 3 plus 0.4 squared times 3. And then this 3 right here is another 3. But I'm going to think of this as 1 plus 0.4 plus 0.4 squared times 3. So I factored out the 3, and I rearranged it so like this 3 comes first, like this 1 comes first, really. There it is. And then the 0.4 and then the 0.4 squared. So this is gross. I'm so sorry. Hopefully, if it doesn't make sense, you can rewatch the video or ask me, and we'll sort of get there. All right, now I'm just going to tell you the pattern that happens if we continue, okay? So MT, it's going to be 0.4 to the T times the initial amount. Fine. Plus, and this is where it gets a little bit gross. I'm going to drop it down here for room. We have 1 plus 0.4 plus 0.4 squared plus 0.4 cubed plus dot, dot, dot. That pattern continues. And when does it stop? Well, for M3, we stopped when there was a 2. For M2, we stopped when there was a 1 on the 0.4. For M1, we stopped when there was a 0 on the 0.4, right? There's no 0.4 there. So when does this stop? It stops at T minus 1. Gross. So all of those get multiplied by 3. Okay, we'll do this. There. Disgusting. There's the updating function. It truly baffles me that, there's like Desmos ones where you can kind of play around with it. So I'll do another video on that. Now there is a slick way to figure out what this is, and it has to do with the fact that if you were to multiply 1 minus x times 1 plus x squared plus, sorry, this should be cubed. So we're going to keep increasing the power, right? This is x to the 0. So then we have 1, 2, 3, all the way up to, let's say, t minus 1. Then what you're going to get, if you work that out, is 1 minus x to the t. So the fact that this multiplication, let me actually move this over. The fact that this multiplication is equal to that, it's kind of amazing. But then you can divide both sides by 1 minus x. And what we find out is that 1 plus x squared plus x cubed plus dot 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 plus x to the t minus 1 is equal to 1 minus x to the t over 1 minus x. So this thing, which is really long and really gross, is equal to this thing, which is not so long. And hey, look, here's a long, gross expression. And this is the case where x is 0.4. So that long, gross expression is the same thing as 1 minus 0.4 to the t over 1 minus 0.4. Which means, oh, and there's no reason you would know this. That is like a, we might eventually talk about that. That's called a geometric sum. Okay, which means mt is equal to 0.4 to the t m naught plus 3 times 1 minus 0.4 to the t all over 1 minus 0.4, which I could have written as 0.6, but whatever. So this is my solution function. And notice how much harder it is than an update. This is kind of the only reason I kept doing this is to make this point. Solution functions in general, very hard to find. Updating functions, oh, no. Oh, bread and butter, baby. Like, come on. We can do this. We can do updating functions, okay? So, anyway. Sorry if you've hung in there this far. Let's just finish this out real quick. Again, I would not expect you to solve for that solution function on your own. That's disgusting, and it uses techniques that you've probably never seen. All right, so how would you describe or teach an updating function versus a solution function? So like the way I do it, I think that like, so updating function is just what you do to update your list. That's it, okay? Solution function, this is like the parent function giving you all the data. This is something, handed down by God. Here you go. Now you know the answer for all possible time. I'm just going to leave this blank. You can put it in your own words, whatever you think. Okay? All right. Here's an exercise I like, though, because it's much more conceptual. So, let f of x be an updating function rule. What does that, what does that even mean? Look, I mean, the next measurement, you have to do some function to your current measurement, right? We've seen examples where the next measurement was your current measurement plus 1.5. We've seen examples where the next measurement was 0.4 times your current measurement plus 3, right? Updating functions, they're functions. You're doing something to a number, and you're going to get a new number. That's a function, okay? And we called the input something gross, but here they're just calling it x. But the function in this case, like in this example, it's x plus 1.5. And the function in this case is 0.4x plus 3. Okay? The function it's the verb, it's the stuff you did to that measurement to get the next measurement. So adding 1.5, that's what I did. So add 1.5. Multiplying by 0.4 and then adding 3, multiply by 0.4, that's what I did. Okay, that's the function. So, all right, there's some kind of updating function. And the way I think of this is m0, you do the function, and you get m1. You do the same function, you get m2. You do the same function, you get m3, and so on, and so on, and so on. Okay? So, that's all they're trying to say here. Now let's read the question. If f is invertible, what does f inverse represent? look, like here's my input to f, and here's my kind of output. And then it'll become an input and become an output, right? So conceptually, sort of the measurement at time t, f will tell you the measurement at time t plus 1. And so remember, the one thing I harped on with inverses is that I just go the other way. This is f inverse. So f inverse, it sort of like tells you the previous measurement. It really tells you how to compute. How to compute the previous measurement. Whereas f, this thing, tells you how to compute the next measurement. Right? So one goes forward in time, the other goes backward in time. So conceptually, that's what the inverse is doing. It's telling you how to compute the previous. So illustrate your answer using the following update. Okay, fine. Let's do that. Here's the idea. Solve for the previous based on, right? So h of t is h of t plus 1 minus 1.5. This right here, well, this right here, this is f inverse. If I promise it doesn't have to be complicated. H of t plus 1. Okay. If this was 10, then this would be 11.5. And you could think of it as, well, I added 1.5 to get there. But if you knew, like, let's pretend for a moment this is like H2, so then this is H3. If you knew in the third month or whatever, it was 11.5, and someone asked you, what was it the previous month? You wouldn't hesitate. You'd subtract 1.5. You'd be like, oh, it was 10. Well, congratulations, you've done the inverse function. Okay, this is why, like, we make things more complicated than it has to be. But the inverse function goes the other way. You're going to undo something. Okay, so now f goes forward in time by 1 unit. So if you do 2 f's in a row, whoop, this is f compose f, you're going to go forward by 2 units. All right, so like if h naught is 1, and I'm going to use this updating function here, so then h1, well, that's going to be 1, that's 2.5, and h2, that's 4, right? But instead of doing like plus 1.5 plus 1.5, you could go straight from here to here by just doing plus 3, right? And so what does that look like? Well, look, first off, the subscript increased by 2, okay? So here's what we're going to do. Let's use what we know. Here's something we know. If the subscript decreases by 1 or increases by 1, however you want to think of it, look, this measurement is the previous measurement plus 1.5. All right, but hey, h of t plus 1, h of t plus, that's this. This is h of t plus 1.5, so that is that, and I still have to do this, plus 1.5. So h of t plus 2, that's h of t plus 3, which is kind of confusing to say because this is not a subscript and this is a subscript, but whatever. So what does doing the updating function twice in a row represent? It represents hopping to the measurement, like not the next one, but the next one. So 2 measurements down instead of 1 measurement down. I don't know. And can you guess what would happen if you did 3 of them? Right, it's going to be 3 measurements down or whatever. So the hardest part of this, you should really think of all of this stuff as we're learning another language. Okay, we're getting used to like, what the heck are they talking about here, and what are they talking about here, and stuff like this. So anyway, we'll handle this more in class, and maybe we'll think of some better ways to describe it. So that's it for this video.